I believe this is where we left off. Is that true? That the last thing we did in our notes is we drew this graph, but we didn't talk about it? Okay. Did I remember correctly that we had bars for each age group? Yeah?
Yes.
Okay, great. Before we answer part F, what is the big thing that my graph is missing?
Title.
Title. Yeah, hopefully you put a title on yours. Okay. So part F, is there an association? Justify. We talked about, yes, there's an association. If there were no association at all, every age group would have the exact same bars. It wouldn't necessarily be even, but they would all be the same. The idea with an association is if I give you information about one variable, it changes the likelihood of another. So in context, if I tell you that someone is 30, it increases the likelihood that they have an iPhone versus if I told you that they were 60. That's what the association means. So when we describe the association, we need to compare the age groups to each other. But we need to do it in a specific manner. It is not okay to say 18 to 34-year-olds have iPhones more than the other two. That's true. It's not specific, though. How much more frequently do they have iPhones? So if we write out a few sentences here, I need to make sure I talk about all three age groups and all three types of phones. And it needs to be done in context. So I'm going to say 18 to 34-year-olds. Have iPhones about 1/3 more frequently than 35 to 54-year-olds. And about twice as frequently as 55 and older. So what is key here is this 1/3 more frequently and this twice. That's the quantifying, bless you, part. Bless you. Okay, if we talk about Android. Okay. 18 to 34-year-olds I'm going to start with again. 18 to 34-year-olds have Androids about 1/3 more often or 1/3 more frequently than 35 to 54-year-olds and over twice as frequently as 55 and up. Yeah, it's very similar. And then last, the other category. Most 55 and older folks have other phones. About 1/3 more than 35 to 54 and over twice 18 to 34-year-olds. Now, I talked about everything. I compared every age group, and I talked about all the iPhone, Android, and others. This is, like, if you really want to talk about everything. You don't need to have all of this, though. So, this is a little bit more less structured, and so our answers are going to differ depending on what you notice versus what I notice. What is really important is that 1/3 more than or twice than. We should not say percentages. So some people like to say, I don't know what these two numbers are. Let's say this is 30% and this is 20%. People will say 10% more. That's not 10% more. 20% to 30% is not 10% more. 50% more.
But that's percentages.
I also don't want numbers. So don't say 7 more people, because we talked about this before. 7 more people, is that a lot? I don't know. Depends on how big your group size is. So that's what I am looking for in the future when it asks, is there an association, and to say what that association is. Okay. Not gonna lie to you, I really am not a big fan of categorical data because there's a lot to write. Do we have any questions on categorical data before moving on? Okay. What we are going to talk about for the rest of class is numeric data. Numeric data is what a lot of our data is going to be, and there is more to talk about. So what we'll talk about today is we are going to display numeric or quantitative data with graphs, and then on Wednesday we will take those graphs or take that data and find numeric summaries. Okay. So first thing to remind you, quantitative data is the same as numeric. That's the term that I use, just because I think quantitative is a little bit of a mouthful.
And numeric is easier to write.
Yes. There are many graphs that we're going to learn. So for categorical data, pretty much it's bar charts. Pie charts occasionally, but it's bar charts, segmented, comparative bar charts. For numeric data, there's a whole bunch of graphs. Before we talk about and make those graphs, one thing that's important is describing the graph. So the graph is one way to display the data, and I'm often going to ask you when you make a graph to describe the distribution or to describe what the graph is showing. And what you're addressing in general is patterns and then any departures from those patterns. There are 4 things that you will talk about. What you need to remember is CSSU.
Wait, patterns.
And departures from the patterns.
Yeah, it feels like I can summarize what a layman might think of when a layman. It just sounds like what you think of when it comes to like statistics off the top of your head.
Well, that's why we're going to talk about more detail. Here's what you're talking about. C, you are going to give an approximation for the center of the distribution. Center is the mean or the median. One of the S's is shape, and we'll talk about that in a minute. The other S is spread. Spread is a measure of the variability in the graph. And U is anything unusual. Oftentimes when we think of unusual, we think of outliers. That's one type of unusual. There might be gaps in the graph. There might be other things as well. The order that you discuss these in doesn't matter. You just need to make sure in your description you hit all 4. Okay, we're going to take a look at some of the following shapes. These 6 are the big ones. A symmetric distribution is exactly what it sounds like. It could be like that. This graph is bimodal. It's also symmetric, though. So bimodal just means it has 2 peaks. So a mode is a peak. A single peak or unimodal, again, something like that. Doesn't have to be in the center, though. You often might hear the term bell-shaped also.
Bell curve.
bell curve. So this one, we can call it symmetric, we can call it unimodal, we can call it bell-shaped, or bell curve, any of those work. Skew is not going to be symmetric. Skew is if you were to take this symmetric graph and take one of the tails and pull it. The skew always follows the tail. So when it says skewed right, the tail was pulled to the right. So that is skewed right. So the skew follows the tail. So skewed left, something like that. And a uniform is just uniform across the top. Big key here is that we don't worry about the little bumps. All we care about is the general shape, the shape as a whole. We don't care about little bumps or little departures from the shape. Okay. So this graph right here is called a dot plot. We saw this on day 1. So this is a dot plot, and it's used for numeric data only. Each dot in this case represents one game of the 2004 U.S. women's soccer season. So this game is one where the team scored 0 goals. Here they scored 7, here they scored 8, so on and so forth. Dot plots only used for numeric data. You're going to be constructing graphs, you're also going to be describing them. So when looking at this, I would ask you, tell me about the distribution of points scored in a game, or goals scored in a game, in the 2004 season. Because this is numeric data, we're going to do that CSSU that we wrote above. So there are 4 things that we need to talk about. We need to make sure that we give the context. So I'm going to start with context. The distribution of goals scored in the 2004 U.S. women's soccer season. Okay, that's the context. It tells me 2 things. It tells me the variable, which is number of goals scored, and then it tells me the who. The who is the U.S. women's soccer team. Okay, so if we talk about center, we're just approximating where do we think either the average is or the median is. What I don't want you to do, though, is just look at the lowest and the highest. So please don't say 0 to 8, well, the center is 4. That's not the case.
That's not how averages work.
Center looks like the median might be about 3. So I'm going to say the distribution is centered around, that's really important, around 3 goals. You have to say around because we didn't actually calculate the center. We're just approximating. We have to talk about shape and spread. If we look at our shape, it looks like we have a peak here. This is a little departure from that peak. That's a little bump. We don't care about that. And then it looks like there's another mode and maybe a slight skew to the right. So the distribution is bimodal. Has 2 modes, it has 2 peaks with a slight right skew. Notice that the word I'm using is distribution, not graph. The graph just shows us the data. Distribution is the word to use. For spread, the spread is 0 to 8 goals with, okay, 0 to 8 is not helpful. All I did was look at 2 data points. That doesn't display the entire graph. What I want to know is where does most of the data fall. So while we go from 0 to 8, most of the games really are 1 to 5. So the spread is from 0 to 8 goals, with most games between 1 and 5 goals. So I want both. Lowest, highest, but then where's most of the data? And then there's nothing unusual. The 6, 7, 8, those are not outliers. Outliers have to be vastly different. So those are not outliers. Outliers have to be vastly different. That being said, we're just going to say nothing unusual. Because then I know that you thought about the unusual part. Okay. Questions, comments? Okay. Besides describing a graph, you need to be able to compare distributions. So that is where, obviously, you're comparing 2 different data sets. You're still going to do CSSU because it's numeric data. There are 2 things, though, that you have to make sure that you do. The first one is that you actually compare. What I mean by that is that you use specific or explicit comparison terms. And then the other thing is you need to make sure you give the context using the variable name. Not just the group names. So here's an example. As you can see, this is a comparative dot plot. So it's 2 dot plots using the same x-axis. We're looking at household size for, let's say, various households. It's a sample of people who live in UK and a sample of households in South Africa. So I would ask you to compare the 2 different distributions. You would say the data is numeric, so we're going to use CSSU. We need to compare. When we talk about center, all I want is you to compare. You don't even need to give numbers. So a lot of times people will try to get fancy and they'll say something like, the center in South Africa is 6 and the center in the UK is 3. Did I actually compare though? No. Do I know that 6 is bigger than 3? Yes. You're not going to get credit though. So don't bother using numbers. Just compare. So I'm going to say the center for household size in South Africa is higher than in the UK. That context part is here, household size. So a lot of times people will say something like, the center in South Africa is higher. You said South Africa and UK, but you didn't actually say the variable being the household size. Okay, if we talk about shape, South Africa is unimodal, so is the UK, so they're both unimodal. Sometimes we want to say, it looks like there's a skew. These 2 data points do not make a skew. They're unusual. If we take those 2 out, it doesn't really look like there's a skew. Maybe a slight skew, but not because of those 2 points.
And
Bless you.
Oh, no distraction.
Both distributions are unimodal. I'm going to give a bit more detail and say South Africa has a slight right skew, whereas the UK is more symmetric. I don't need to mention household size in every sentence. As long as it's there once, I'm going to get credit. If we talk about spread, again, don't get too specific. All I want to know is which spread is bigger. Which country has a bigger spread? Which country has more variability in the data set?
South Africa.
South Africa, right? That's all I want. You don't have to give any numbers. So the distribution for South Africa has a larger spread. And then the UK has nothing unusual. South Africa has 2 outliers, or you can say unusual observations. I want to know why they're unusual, though. So these are 2 outliers with much higher household sizes than the remaining observations. So that's a good word for you to know and to use. We really should not be using the word points. So I don't want you to say there are 2 higher household sizes than the other points. We don't use the term points. We use the term observations. Okay, questions on comparing. The biggest thing that people get tripped up on is they don't compare. Giving numbers is not a comparison. So I would say, I like to be efficient. I don't even give numbers because they're not needed. We good to go on and talk about more graphs?
Almost.
Okay, we're going to do a little bit of skipping around. I don't think we have time for the second page, so we're just going to skip right on past that. That's an example. If you can find this page, this is the last thing that I want us to do. So you will note, I don't even need you to read at the top. I don't even care if you know what the context is. All I care is that you look, notice each graph has a label. So the first dot plot is A, the second dot plot is B, so on and so forth. You are just going to take 3 minutes with the person next to you and do 1 through 4, just writing. Honestly, on mine, I wrote like 2-word answers for each. So good luck, take a few minutes. Okay, I know you're probably not finished, or maybe you are. Let's talk real quick. Question 1, what is the most important difference between A, B, and C?
The placement of the centers.
Center, yeah, all I'm looking for, center. Question 2, what is the important difference between C and D? Spread, center, spread. 3, what are the 2 biggest differences between D and E?
Outlier shape.
Shape,
Spread.
spread. Okay, did you notice though that D and E have the same lowest point and highest point? But their spreads are not the same, do we agree? That's why I said you can't just look at the lowest point and the highest point, because that's not a good reflection of spread. So the biggest difference is spread, shape, outliers, all those. And then 4, the most important difference between C, F, and G. Shape. How'd we do? We're going to go to this page instead, so if you could find this one. Next thing that we are going to talk about is a stem plot. Stem plot is for numeric data only. So when you're describing it, you're going to do CSSU. Important things to remember. Label the variable. And you need a scale and a key. And so we have this data set here where we are looking at the number of shoes that people have by gender. So on the left, we have a random selection of, I don't know, I think it's 20 people, 20 females, how many shoes they own. On the right, 20 males, how many shoes they own. So we are going to make a stem and leaf plot. So a stem plot or a stem and leaf plot. I am going to start with the male distribution on the right. Let's just ignore the female distribution for a minute and look at just the data set on the right. The way a stem and leaf plot works is you put numbers in what's called the stem, and you have numbers in what's called the leaf. The stem, I'm going to put the tens place. So if I look, my smallest observation it looks like is 4, and the highest observation it looks like is 38. So if I look at the stems place, or the tens place rather, I'm going to go 0, 1, 2, 3. I'm going to tell you we're going to need more space, so leave some space down here. But this would be 0, 4, right? So this 4, the tens place is a 0. So then what I'm going to do is I'm going to find all of the observations in this data set that have a 0 in the tens place. And those will all go in what's called the leaf. So this would be 7, 6, 5, 8, 7, 4, 5, 7, 5, 7. Generally, we put them in order. So I have 4, and then it looks like there are 3 5s. So then I'll do 5, 5, 5. You do not put commas.
Yeah.
There are no commas.
And that was anyone that started doing it.
There's 1 6. I think there's 4 7s. And then there's an 8. When I go down to the next row, this is all of the numbers where there's a 1 in the tens place. So that would be 14, 10, 11, 12, 10, 10, 10. Again, you're going to put them in numeric order, and you're going to try to line your digits up. So there are 4 10s. There's an 11, a 12, and a 14. Do we see what I'm doing? Yeah? Okay, there is a 22, and there's a 35, and a 38. That is a stem and leaf plot. You still need a title, and you need a key that tells you how to read this graph. There are 2 different ways to do the key. One is in words. I'm going to say the stem is the tens place, and the leaf is the ones place. That is one way to do the key. The other way to do the key is to just choose one observation. So I'm going to choose, let's say, this one right here, the 2, 2. And I'm going to say 2-2 is 22 shoes. Or it's 22 pairs of shoes. But I like this because it looks nicer. I think a lot of people like this because it makes more sense. I don't care which one you do. So you always need a key. If I were to ask you to describe this, this is pretty much a dot plot. All you're going to do is kind of picture tipping it sideways and talk about CSSU. So there's a skew to the right. The center looks like it's about 10, the spread and the shape. Questions? Okay. The reason we like a stem and leaf plot, A, they're easy to construct. B, they can be used to compare. And so you might have realized or thought ahead that I'm going to compare males to females. So now I'm going to do the female distribution on the left. The smallest number I think is 13, and the largest is 57. So that means I'm going to need to add 4 and 5 in my stem. We are going to read from the inside out. So on the female side, we read this way going out. So the smaller numbers need to be near the 1. So I have 13, 19, 13, 15. So we're going to start with the 13, then the 15, then the 19. So there are 3 13s. So it'll be 13, 13, 13, 15, 19. And again, you're not putting commas. And then there's a 22, a 23, a 23, a 24, a 26, and a 26. And you're trying to use consistent scaling. There's a 30, a 31, a 34, and a 38. There's a 49. There are 2 50s, 51 and 57. So this is what is called a back-to-back stem and leaf plot. Used to compare male to female. Questions? Okay, some things to know. There is something called split stems. So sometimes if you have a lot of data that's concentrated, so like here in the male distribution in the 0 and 1, there's a lot of data. Sometimes to see the shape better, we will split the stems. And so one way that's often used is that 0 would be split into 0 low and 0 high. And so that's how it would look. And then your 1 low and 1 high. And you would have that in your stem. The low is anything 0 to 4, and the high is anything 5 to 9.
Rounding rules.
That is really just a way to see shape better. The other thing to know is that we generally only put 1 digit in the leaf. So let's say that we were looking at numbers in the thousands, like word count on an essay, let's say. And let's say from those essays, we had a word count of 1,000 all the way to 9,750. In all likelihood, what we would do is we would put the first number in the stem, we would put the second number in the leaf, and then everything else you can just ignore. So you're not rounding, you're just ignoring. So it would be 9/7, ignore those 2 numbers. Do you guys know the term for that? When you just drop them off? Starts with a T. No, you've never heard that one before? That's called truncating.
That was the word I thought of, but I wasn't sure. But I
Unsure.
but I did not know what it meant, if it was applicable here.
So that is the idea with a stem and leaf plot. Okay. Got 2 more graphs to talk about. I know, I'm excited too.
I gotta go.
You can go. Just grab a pass. Questions on the stem and leaf? No. Great. You're actually going to make the next graph because I'm tired of talking and I think you're tired of staring at me and watching me talk. This table presents the average points scored per game for 30 NBA teams in a recent season. We are going to make a dot plot for the data, and then we are going to make a histogram for the data. Okay, somebody asked about this question before, is what do we do with these decimals? So like 96.5, do we round it up to 97? 96.9, do we round it up to 97? we don't care about these individual data points. We care about what they look like on a graph. So could you round? Sure. I'm not going to. What I'm going to do is I'm just going to truncate. So I'm just going to ignore all of the decimals and only look at 98, 96, 96, 93, so on and so forth. If we were going to do a dot plot, you would have the points scored per game. I made a dot plot. Are you okay if I just read out to you what this dot plot looks like so we don't actually spend the time to do it? I will tell you your number line needs to go from 93 to 106. So why don't you take a minute to do that? Bless you. Okay, you ready for me to tell you how many dots there are? At 93, you're gonna have 5 dots. At 94, you're gonna have 4 dots. At 95, you're gonna have 2. At 96, you're gonna have 3. At 97, you're gonna have 2. At 98, you're gonna have 3. Nothing at 99. At 100, there are 2. 101 has 1. 102 has 1. 103 has 1. And then there are 2 at 106.
I missed the first part. Is are you rounding to the closest whole number?
We truncated.
Oh. So you just lopped off the decimals? Okay.
Okay.
Wait, then. Wouldn't that mean you both have a 105?
Is there a 105? Oh, maybe I rounded then. Yeah, there should be a 105. Okay. You all are going to make a histogram. A histogram is just like a bar chart. But it's for numeric data. So I already made categories for you. You're going to probably need a table. Our intervals are going to be 2 wide. So the first interval will go from 92 to 94. The next one will go from 94 to 96. The last one is 106 to 108. Here's what this notation means. This first interval does not include 94. It goes up to 93.9. And then as soon as you hit 94, that goes to the next interval. So this second interval does not include 96. 96 will go in the next one. So what you're going to do right now is you're going to, with the person next to you, count up the frequency for all of these intervals, and then you will make your histogram. The only difference between this and a bar chart, remember how we talked about in the bar chart there's space in between the bars? It's not the case for a histogram. For a histogram, your x-axis is just a number line. Okay. Right now, move your desk with the person next to you and take, 5 minutes. Okay, let's start talking. You may have finished, you may not have. Did you get a graph that looks generally the same as mine? Or very similar at least? Like I said, I didn't truncate, I used the decimals, but it actually probably doesn't matter. Mine doesn't have a title. Hopefully yours does. I don't care what the title is. A lot of people forget this label on the x-axis. A lot of people just put the numbers. They forget the label, though. What do these numbers represent? They represent points per game. Frequency should be on the y-axis. I should have put some numbers here, but I didn't. Remember, y-axis has to start at 0. The x-axis does not. Does not matter that I started at 92.
How did you get 5 for 100 to 92?
Should it not be 5? Should be 3? Wow. Apparently I miscounted. That's how. Thank you for asking.
Should there be space in between data and the y-axis?
Doesn't matter. Yeah. So question was, should there be space here? It doesn't matter. It does matter to me that there's not spaces between the bars. So you look at this and you know immediately that it's a histogram because there's no space.
Yeah,
As soon as I see space, I'm going to think it's a bar chart.
I put a little space in between the y-axis and the opening just for ease, just for my own ease of.
Totally
grading
good.
it.
We got a few more things to write down, and then we will be done. Sound good? Okay. Next page, constructing a histogram. We already did that. So there's really nothing that we're going to write down here, except I want us to remember that a bar chart is for categorical data only. And remember, that's where there is space. Just a space in between the bars is a bar chart. Few things to know about a histogram, though. We should have equal class widths. That is very important. Class is just the interval. So all I'm saying is the intervals should be the same width. All of our intervals went by 2. You're not going to go by 2 and then 1 and then 2. Can't do that. Got to be the same width. When you're making a histogram, you can use relative frequency or you can use frequency. I'm going to be honest, I use frequency because I'm lazy most of the time. The only time when you're going to use relative frequency instead is when you are comparing. So AKA when you have 2 data sets. So if we were looking at the points scored per game for 2007 and 2010, we're going to need to use relative frequency. So you're going to use relative frequency if you are comparing. And then what do you need to remember? All the same normal stuff. Label, put a title on, things like that.